Hi everyone. So in this session, I want to start the next topic, which is rapidly varied flows in open channel flows. So rapidly varied flows occur when the flow depth changes rapidly over a short distance. So we show that with, as you might remember, the depth of the fluid, which is y, dy over dx, is changing rapidly. So this dy over dx or change is about one, order one, or even greater than that. So this is what we call a rapidly varied flow, and here you can see an image of that, in which, as you see, the depth of the fluid or depth of water is changing rapidly within a short distance. Okay. um, so flow may change from shallow high speed water to a deep low speed condition. So it could be like we have in upstream we have a high speed flow which is shallow, and in the downstream we have a low speed but deep kind of channel or deep water depth. So this is a definition of rapidly varied flows, which we also included at the beginning of open channel flow discussions. And so let's look at a particular case of rapidly varied flows, which is very relevant, especially in the context of civil engineering, and that is hydraulic jump. So when the fluid depth changes very rapidly over a short distance without any change in the channel configuration, sometimes we see these hydraulic jumps, right? So this is called what is we call a hydraulic jump. So hydraulic jump can occur in a lot of different applications. So it can occur either during the change of the channel configurations, for example, the width of the channel, which is something we don't investigate here. But a more commonly ones that is pretty important in civil engineering is when we have a constant channel configuration, for instance, a rectangular channel, and then we suddenly observe these rapid changes over a very short distances. So this is an example of a hydraulic jump where you have slice gate, then you have subcritical flow, and then suddenly it becomes supercritical here, and then suddenly you observe this hydraulic jump where it changes its regime to a subcritical regime. So and you see a lot of turbulence here. A lot of turbulence occurs here. So as you see here, this is what we call hydraulic jump, and discontinuity in the free surface elevation, as you see, and dy over dx goes to about infinity because this is very sharp change, and this discontinuity always occurs from a shallow, which is here, to a deeper depths. And this is what we always have a step up and not any step down, right? So this is like a step function, but it's always up. um, this is what we call hydraulic jump, right? So the hydraulic jump is something like this, and it occurs when there is a conflict between the downstream and upstream influences. So when you have, for instance, in your downstream you have a subcritical regime, and in your upstream you have a supercritical regime, then this hydraulic jump has to occur in order to provide a mechanism for transition between these two regimes. So between a supercritical regime and a subcritical regime. So hydraulic jump provides a mechanism for transition between a subcritical Froude number equals to is smaller than 1. So this is subcritical regime, and a supercritical regime where the Froude number is greater than 1, right? So this provides a mechanism for the transition between these two regimes. And the simplest form of this hydraulic jump, as I said, occurs in a rectangular channel, and we want to investigate that and find a formula for the variation in depth in this type of phenomena. Okay. So this is this is, for instance, a hydraulic jump that occurs here. We are going from a supercritical regime to a subcritical regime, like from a shallower depth to a deeper depth, okay, y1 to y2. And we make some assumptions for driving the relations for between y1 and y2, okay. So first we assume the flow is nearly uniform at sections 1 and 2. Nothing about here, this transition region, but just at section 1 and 2, we assume the flow is nearly uniform. So I just write V1 and V2, uniform flow. It's steady at these two sections and it's one-dimensional, okay? So we don't consider two higher dimensions like 2D or 3D. So by these assumptions, we start writing the momentum equation in the x direction for this controlled volume, this dashed line that you can see here. So we start to write the momentum equation in the x direction, in the flow direction, and this is y. Also, we make another assumption that we neglect the wall shear stress tau W between section 1 and 2 because this is a relatively short distance, and so we can assume that the wall shear stress is negligible or small because as you remember, this hydraulic jump occurs within a very short distance. Okay, this is just for simplification to make our equations are simpler. So we write the momentum equation in the x direction, which is the flow direction for this control volume, this dashed line here. So the sigma f, the sum of the forces exerted at this control volume is F1, the for hydrostatic pressure force at section 1 minus the hydrostatic pressure force at section 2. This equals to like MA, something like Newton's second law, but in terms of fluids, we are going to write it as rho Q V. So rho Q V2, which is going out of the domain. So out of the control volume, so that's why it has a positive sign, minus rho Q V1, which has a negative sign because this is coming into the control volume. Okay. And this is the mass conservation, which I'm going to go through it, but just for simplicity, I'm going to write Q1 equals to Q2. Instead of Q, I'm going to write Y1B times V1. This is just A times V1, and B is the width. And let's see what is the hydrostatic pressure force. Okay, let's calculate that. So here we have this section. If this is section 1, this is section 1. So we have a width of the channel, and this is like a rectangular channel. This is the width of the channel, and this is Y1, the depth of the water here. And so the hydrostatic pressure is gonna look like something triangular here. So rho G Y1 at the bottom. And so F1, which is hydrostatic pressure force, is gonna be 1/2. This is the area of this rectangle. 1/2 rho G Y1 times Y1. Okay, so it's gonna be the area of this one. And then we have to multiply this by B, right? We have to multiply this by B to get the total force on this control volume side. So it's gonna be 1/2 rho G y1 square times b, right? And similarly, we can find F2 is gonna be the hydrostatic force here, 1/2 rho g y2 square times b, right? So this is gonna be the area of this. And so now that we have a hydrostatic pressure forces, we just substitute them into momentum equation. And what we get is 1/2 rho g y square b minus 1/2 rho g y2 square b equals to rho q, instead of qi I'm going to write y1b v1 times v2 minus v1. So first of all, rho is going to cancel out in all the terms. The density is going to cancel out. And secondly, b, which is the width of the channel, is also going to cancel out in all the terms because I have that. So I'm only left with this, which is y1 square over 2 minus y2 square over 2 equals to v1 times y1 over g, I bring the g here, times v2 minus v1. Okay, so this is the first equation, equation 1, which is the momentum equation for this controlled volume. The second equation is conservation of mass. So we know that the flow that is coming into this control volume or into section 1 has to go out of it here. So Q1, the flow rate here equals to flow rate here. So Q1 equals to Q2. And instead of Q1, I can write Y1, this is A times V. This is the definition of Q. So it's going to be Y1 times B, which is the area here, times V1 equals to Y2B times V2. And B is going to cancel on those both sides of the equation. And so this is going to give me the second equation, which is Y1 V1 equals to Y2 V2. Which is coming from mass conservation. And then the third equation is energy conservation equation between section 1 and 2. So I can write it as this: y1 plus v1 square over 2g equals to y2 plus v2 square over 2g plus hl, which is head loss. Okay, and head loss, as we said, we neglected wall shear stress. And the main source of head loss here in this problem is due to this violent turbulent mixing that occurs here. Because of this turbulence, dissipates a lot of energy here. So that is why we have head loss here. Okay, so if you have energy here, if your energy level is somewhere around here, because of this turbulence, it's gonna reduce here to something like this, and this difference is gonna be your head loss, the head loss in the system. Okay, and this is because of this significant mixing and turbulence, turbulent dissipation that occurs here. Okay, so now we have these three equations: equation from momentum equation, from continuity, and from energy conservation. So we want to solve these three to get a relationship between y1 and y2 before and after a hydraulic jump. So an obvious solution for this system, if you see, is y1 equals to y2, v1 equals to v2, which is going to give you 0 here, and hl equals to 0. Okay, this is an obvious solution for these three equations. But as you see, this means that we don't have any jump, right? Because y1 is going to equal to y2. So this means that there is no change in the system. Like simply, we have the same system, okay, from section 1 and section 2. So this is not the solution that we want. And the solution we want is y1 should be different than y2. Okay. In order to do that, I'm gonna use a mass conservation and substitute this into the momentum conservation. So from equation 2, I can say that V2 equals to Y1 over Y2. So I have V2 here. I substitute this into this equation. So just to remove V2 from this equation. So I'm going to get y1 squared minus y2 squared over 2 equals to v1 y1 over g times, instead of v2 I'm going to write this, so I'm going to write y1 over y2 times v1 minus v1 equals to, so I factor out v1 from here, and so I will get v1 squared times y1 over g y2 times y1 minus y2. Okay, I factored v1 over y2 from this parenthesis, and I got this this term. So these two on the left hand side, instead of y1 square minus y2 square, I can write it, this is like an algebra, y1 minus y2 times y1 plus y2 is gonna give me this over 2. This is from the left hand side, and this is from the right hand side, v1 square times y1 over g y2 times y1 minus y2. So these two terms, y1 minus y2, is going to cancel out from both sides of the equation, and I'm going to get, I will bring this y2 here on the left hand side, so I'm going to get y2 times y1, and also I'm gonna bring this y1 to the denominator, so I'm gonna get y2 times y2 over y1 times y1, y2 over y1 times y2. So these two terms are gonna cancel, equals to 2v squared over g. So I also bring 2 to the right hand side, and then I get this equation. Okay, so then I divide both sides of this equation by y1, so I'm gonna get y2 over y1 plus y2 square, this is y2 square over y1 square, equals to 2v1 square over gy. And if you remember, the definition of Freud number is v1 over the square root of gy1. So here, instead of v1 square over gy, I can just write Freud square. And this Freud is at 1, at section 1, or at upstream. So I rearrange this equation. I get y2 over y1 square plus y2 over y1 minus 2 Freud number to power 2 Freud number square equals to 0. So this is a quadratic equation, right? So I can use quadratic formula in order to get the answer or solution for this. So assume this is like y2 over y1 is x. So this equation is actually x squared plus x minus this 2 Freud number 1 square equals to 0, right? So this is this equation. So this is a quadratic equation. I can solve this. I have an I know the solution of this kind of quadratic equation. So x or y2 over y1 equals to 1/2 times minus 1 plus minus square root of 1 minus, which is going to be minus 4 times AC. So this is 4 times 2 times 1. So it's going to be 8 Freud 1 square. Okay, so this is the solution of this equation because this is a quadratic using quadratic formula. And as you can see, the negative solution is not possible because the negative solution means that y2 over y1 should be less than 0. It should be a negative number, which doesn't make sense, right? This is an unphysical solution. So the only possible solution is y2 over y1 equals to 1/2 minus 1 plus square root of 1 plus 8 Freud number 1 square. And this is very important formula for hydraulic jump. As you can see, we found a relationship between y2 and y1, so the depth before the jump and the depth after the jump, in terms of the Freud number at the upstream. So the Freud number here. So if you know the Freud number here, you can guess and you can find what's gonna be y2 after a hydraulic jump occurs. Okay, so this is very, very useful and very important formula in the hydraulic engineering applications. Okay, so let's examine this equation further. So if Freud number is greater than 1 in this equation, you can calculate and see then y2 over y1 is gonna be greater than 1. Okay, so if Freud number is greater than 1, y2 over y1 is gonna be greater than 1, and this is what we call a hydraulic jump. And so this produces a hydraulic jump, right? So the y2 is gonna be greater, and then you will see a jump in the fluid. So this only occurs if Freud number is greater than 1. But is it possible to have a Freud number less than 1 and then get the hydraulic jump? In order to answer this question, we have to look at energy equation. So if you go to energy equation, you substitute this into energy equation, which is shown here. What you get is HL over Y1 equals to 1 minus y2 over y1 plus Freud number 1 square over 2 times 1 minus y1 over y2 square. So this is just manipulation and rearrangement of energy equation. You will get to this, and also removing v1 and v2 from your equations, you will get to this equation. So if Freud number 1, upstream Freud number, is smaller than 1, okay, then you will and from this momentum equation you will see if your Freud number is smaller than 1, so this one should be smaller than 3, right? If this is smaller than 1, this is 8 plus 1, 9, square root of that is going to be 3, so this one should be smaller than 3. Minus 1 is going to be 2, so this term should be smaller than 2, so y2 over y1 should be smaller than 1, okay? So if Freud number is smaller than 1, y2 over y1 is going to be smaller than 1. And if you substitute these here, you're going to get that HL will be negative for this condition. Okay. So the other way is not possible, never going to happen, because HL smaller than 0 means negative head loss, and it's not possible from thermodynamics law. So we can go from here, from a shallow supercritical channel to deep subcritical slower flow regime. This is possible in nature, but the other way around is not possible. Okay, so we cannot go from a subcritical regime to a supercritical regime, and this is because of the thermodynamics law and because the fact that HL is gonna be smaller than 0 or negative. Okay, so now let's draw this relation here to get more familiar with that and see how does this look like. So if you draw it, you will see y2 over y1, and on the other axis we have Freud number, upstream Freud number, which is v1 over square root of gy1. So you see when upstream Freud number is smaller than 1, and for y2 over y1 is smaller than 1, this place and this area is not possible, right? Hydraulic jump is not possible. It's impossible here because of this thing that we showed here and also this negative head loss. But once your Freud number, upstream Freud number gets bigger than 1, then you get this. So for Freud number equals to 1, y2 over y1 is 1, right? We saw it here. If Freud number is 1, this is going to be 3 minus 1 is going to be 2 over 2 is going to be 1. So this is one point of that equation. And then you can plot that for multiple points, and what you will get is this graph here. So which shows the ratio of the depths after hydraulic jump over the ratio before the hydraulic jump versus the Freud number, upstream Freud number. Okay, so this was the main discussion, main formula for hydraulic jumps, which are very important for designing many open channel flow systems. And next time I'm going to solve an example for this hydraulic jump problem. Thank you very much.